Hi, I'm Arin, founder and CEO at WebRTC Ventures. In this presentation today, we're going to talk with you about architecting your WebRTC application for scalability. So my colleague, Alberto Gonzalez, our CTO, will be talking as well in the second part of this presentation. I'll start out with discussing a few different common architectural patterns at a very high level that you can consider, and then Alberto will fill in some details on different media servers and architectural use cases for you. Now, the first thing to know about building your WebRTC application is that when you first start to research the topic of WebRTC, you see a diagram, something like this, a little misleadingly simple diagram, but it's certainly accurate. It shows that between your two peers, you end up establishing a peer-to-peer connection. There's no server in between for the video, the audio, and the data channel, and you can have a complete RTC peer connection between just those two users, and you just need a signaling server to help establish that connection. And at its simplest level, that is a WebRTC application, and it will certainly work that way. However, in the vast majority of scenarios, especially if you need to scale your application to a large set of users, you're going to need to implement something much more complex than that. And so you need to consider all of these factors here that I've listed around scaling your application, handling different network connections like stun and turn, browser and mobile support video codecs. And so generally speaking, you're not actually building something this simple that is a true peer-to-peer connection. You've probably got some media servers and other things in the middle. We'll talk more about that. There are, generally speaking, four ways that we would say you can build your live video application with WebRTC. The first is directly against the standard. So you're basically building your own WebRTC stack here. The second is what's referred to as unbundled WebRTC, where you're handling more about the codecs and the transports yourself. Third is to use an open source media server, which it in turn is implementing the WebRTC against the WebRTC standard for you. And the fourth option is to use a commercial platform, a communication platform as a service. So we'll talk through some pros and cons of each of those over the next few slides. The first option is to build directly to the WebRTC standard, to build your own stack, essentially. Gives you a lot of power, but also requires a lot of responsibility and a lot of work. You're going to have to compile a WebRTC lib, which is no simple task in itself, as well as handle stun and turn servers so that you can make connections over various network connection scenarios and get across firewalls and things like that, as well as the application signaling that you need to do yourself. You're going to have to handle everything about doing any sort of scaling on group chat, because beyond a few users, you're going to start to run into performance issues. So you need to implement that yourself, maybe build your own media server to go in there, especially if you want to build in other capabilities like recording or transcription, etc. So building against the WebRTC standard is definitely an option, but a pretty complicated one. Now, if you do need more power and more control over some of the lower level aspects of what's going on in a live video call, you could also consider unbundled WebRTC. These diagrams are adapted from a presentation that Sahi Levi did on WebRTC Live, which we produce at WebRTC Ventures. And he talked about the typical WebRTC media processing pipeline, where you're capturing that audio and video from a user, encoding it, sending it over to the other user. Could be over an RTC peer connection directly, but most likely you're going to have a media server there in the middle, which then in turn is helping with the receiving, and it then needs to be received and decoded on the other user's end as well. Now, if you want more control over that pipeline, say something about your use case, maybe you do something, you want to do your own encoding and decoding mechanism, or about the transport to handle, how do you balance, say, latency versus quality in the call, and you want to handle those trade-offs yourself and do something more unique to your use case that really allows you to differentiate your product from something that anybody else is doing. That's a sort of scenario where you're thinking, well, I wish WebRTC would do this instead. that's sort of scenario that you might want to consider an unbundled WebRTC application, because you can use the web transport and web codecs APIs to do that sort of low-level manipulation yourself. Third option is to use an open source media server. These various projects will handle a lot of things for you, like the details around the video and audio itself, partner all of the signaling to establish the calls. They may have stun and turn built into them, or you can incorporate other open source projects to do that for you. They probably have some form of scaling capability built into them already, maybe for specific use cases. So depending on the use case you have, you might choose one open source media server over another. They're probably based on an SFU or maybe an MCU media server architecture, and they've got a lot of things already built into it for support in different desktop and mobile browsers. So does a lot of things for you, which is great. So it's going to be much simpler than working directly against the standard. However, you are still managing all of that infrastructure yourself, which is a pro and a con. You are responsible for handling all updates to that infrastructure from the open source media server itself, from that project when it has updates, as well as controlling how you scale those cloud servers that you run the media servers upon. And there's a lot of different options to consider here. Some of the most popular options for open source media servers are the Janus WebRTC server, Jitsi, Media Soup, Pion, as well as LiveKit, which is built upon Pion. Now, the fourth option, the final one I'll mention, is CPaaS. And so these are generally commercial communication platform as a service. They're going to handle a lot of things for you, which is great. They're going to handle all of the support for different browsers around WebRTC standard. They've got media servers built into that you don't need to think about. Those media servers are probably already on a globally scaled, widely distributed network, so you don't have to think about any of those things. They've got stun and turn handled. They've got the web desktop and mobile browser support handled for you. And they've probably got some other features built in that you're going to find useful, like recording or additional APIs for SMS, text messaging, voice, VoIP interconnections, transcription, etc. However, you pay for these according to usage, either per minute or per user or bandwidth type of scenario, which does tend to make it the more expensive transactional option. And there are a lot of options to consider here again: Agora, Amazon's Chime SDK, Daily, LiveSwitch, Twilio, and Vonage. All great options to consider for different scenarios, depending on what works best for your particular use case, language or library support that you need, billing model that you need, etc. Now, which one of these solutions is right for you? It depends. It really is all about different trade-offs. And so the way that we recommend you consider these trade-offs is a few different parameters here. What is your appetite for the upfront cost? How much is it going to cost to build this application? Using one of the commercial CPaaS solutions is probably going to be the lowest upfront cost, just because they have so many features built in for you already. And you don't have to worry about anything about the media servers or the infrastructure around that itself. Other end of the spectrum would be building directly to the WebRTC standard, where you're going to have to handle all of that browser, mobile support, scaling considerations, all of that yourself. So that's going to probably be the highest upfront cost. The other type of cost that's very important to consider, though, is ongoing cost. What does it cost per call, per conversation on your platform? And the model for that's going to vary very much with your use case. Generally speaking, the commercial solutions are going to have the highest transactional cost for you. And open source media server solutions are going to have a much lower transactional cost, because in that scenario, if you're using an open source project, there's not really a license fee involved. You're really just paying for the amount of cloud servers that you need to run those media servers. But on the other hand, you are also handling everything about scaling those cloud servers. So although the transactional cost of the servers is going to be lower in an open source scenario than a commercial CPaaS, you also need to keep in mind that you need to have more in-house professionals in DevOps and scaling of infrastructure. And so depending on the scale that you're at, depending on your specific use case, you need to factor in all of that, not just the cost of the media server, but the cost of your staffing for the DevOps and support around that. But certainly at a certain level of scale, that's going to be cheaper on a transactional basis for you to manage that in-house than with a commercial service. Also should consider the technical difficulty of working with that and the number of features that are going to be included. So again, the technical difficulty of working with the WebRTC standard directly or an unbundled architecture is going to be much higher than an open source media server or a CPaaS that's handling all of those things for you. And those open source media servers and the commercial solutions are going to have many more features included for you as well. So lots of trade-offs to consider here. And within each of these categories too, once you've made the choice of which of these high-level architectural paths you want to go, there are many different options within them to consider. So next, my colleague Alberto will talk with you more about different media server options and architectural use cases and scaling patterns.
Hi, as Arin mentioned, there are different alternatives to build a WebRTC application. In most cases, direct peer-to-peer is not an option. In this diagram at the right, you can see a representation of how an 8-participant peer-to-peer network would look like. Without an intermediate media server helping us, it's a bit messy and especially resource intensive. To reduce the amount of resources used at the edge, there are two popular architectures used to scale this. So we have the SFU architecture and the MCU architecture for scaling WebRTC applications. The MCU, or multi-point control unit, handles mixing of video and audio streams in the central server. So each participant only handles a single stream. On the contrary, SFU, or selective forwarding unit, each participant only connects the SFU, but receives unique streams for each participant. Both of these approaches allow us also to record, broadcast, or even interface with other services like transcription or VoIP legacy systems. On the MCU, as I mentioned, the streams got mixed in the server side, so all the processing is moved towards the server. In that case, that's more lightweight on the client side. And as you can see at the bottom, these are just some popular MCU open source media servers. The SFU, in this case, does a hybrid approach where each participant will send just a single stream, just like in the MCU, but in this case, the streams are not being processed or mixed on the server, they are just relayed or forwarded. What this will allow is a reduction of CPU usage on the server side, but in exchange would require a little bit more CPU usage on the client side. This is a very popular approach used today, and also this allows for end-to-end encryption. There are many popular SFU media servers, open source, but Jitsi is just one of them, Janus, LiveKit, and MediaSoup. All of those are pretty popular. So now, how do we scale beyond a single MCU or SFU server? It depends on the use case. Media processing are in WebRTC is pretty CPU intensive. For example, a X-large AWS instance can handle more than a couple hundred media streams. So what happens if we have 1,000 viewers. A single server cannot handle it, so we need to follow an architecture that would look like this one, where the publisher or the group of publishers send their stream to a single server, and this server, potentially a SFU, would be relaying that to the other servers, and that way we would be able to handle larger amounts of viewers than we would with a single server. And what about other use cases? How we go beyond a single media server? So another common use case is multi-party video conferencing, and today everyone would expect that we should be able to handle 50 or even 100 participants on a single client application. That's quite complex, and it sometimes might require this type of architecture that I'm showing here, where also, again, we are using more than a single media server to handle a single video room or video chat. We are showing here an SFU, but an MCU could be also used. It's just perhaps a bit more challenging. And there are smarter ways to do this, but this is just one approach. And another kind of typical use case is when you want to have many small video calls, but that need to be concurrent. So you need a lot of horizontal scalability. Well, in this case, I also included some examples of how that would look like if at the same time we try to integrate with a SIP legacy network or IP PBX system. In this case, at the left, you can see the web publishers connecting to perhaps an MCU or SFU. We can decide based on our preference and different requirements. And at the other side, we would have the phone caller calling through the PSTN and reaching the PBX and then relaying that RTP stream to our SFU video conference. To be clear, this architecture is much more complex than what it looks here. There are many potential challenges. The SIP implementation, the supported resolutions, RTCP maxing, sometimes might be not supported. There are different codecs used in SIP telephony legacy systems and on the web. There are different preferences. So that all these things will play out in deciding which architecture to follow. So in kind of conclusion at this stage of the presentation, for large video conferencing architecture, there are a few considerations I want to comment. One is, well, very important piece is really the integration of VoIP legacy systems. That's kind of an important challenge, and you need to consider if you really need it or not at the beginning. That might influence the architecture that you want to build. Also recording and voicemail or this type of speech-to-text capabilities. That also, for example, would force you to have a media server. Also, we want to know what's the number of participants we want in the call. Having small groups, of course, is much easier. And larger groups would require an architecture like the one I showed 2 slides before, where there were 2 SFUs for a single video room. But now, how we orchestrate this, how does it look like? One proposed architecture could look like this one in this slide, where we would have initially the actor, which is the web user, just initially authenticating with a dispatcher. This dispatcher could be just a REST API if you want, and would be also in charge of maybe scaling the different pods or nodes that we have, and also would be able to distribute redirect us to the right media server. So initially we would authenticate point 1. Then we would initialize the signaling. In this case, we are going to the right node. We are starting to have some type of signaling communication with the wrapper node. And that could be, if you want, a WebSocket service. That's a pretty common approach. And that way we are already connected to a service that will allow us to communicate in real time. To be clear, the wrapper is not the media server, it's just the application logic of it. And then once we are ready to call, we would be communicating through the wrapper with other participants, and then media would flow to the SFU media server in this case. So this is an interesting approach. It's pretty common, and it helps to decouple a little bit the logic instead of having a single point of failure and a single big monolithic application. In this case, you break it down in some different pieces. So again, some of the challenges and why we would propose this very high level architecture sometimes is because it decouples media server from application logic. Of course, it still has a stateful system. Finally, WebRTC, if you are always connected to other participants and sending live video, so it's stateful. It matters to who you connect with, and it has some complexities, and that's why we have these services like Dispatcher and Node that help us handle that for the media server. And of course, also we have different blocks here. You can see block at the top with wrapper node and SFUs, and a second one saying wrapper node and SFUs. That just symbolizes that we would, of course, have many replicas of that kind of pair of services together, and that would allow us to auto-scale or down-scale based on needs, so we can be more efficient in terms of cost in the cloud especially. And of course, when you don't want to over provision when you are handling very expensive services. Another important piece when scaling is, if we want to be efficient, when we want to use auto-scaling rules, as I was mentioning. These rules would look like the ones I'm explaining here at the left. So we would use a connection threshold for auto-scaling. So in this case, in this diagram, I assume the connection threshold is 100 connections for this specific server, and that threshold is what will indicate that we need to auto-scale. Also, an important part is to know the maximum number of sessions per room, the server sessions per server that we can handle. And also we want to make sure that we have a limited users per room as well, and we need to predict that in some way. Of course, we need to define it to have some type of estimates. And also another part is to be able to have the new server ready when we need it. And of course, it all depends on the spikes, on how many users will join and how fast they will join. So in this chart, I just showed two examples. One line is going at a piece of 2 users per second, and the other one at a piece of 5 per second, the orange one. So if we were at a piece of 2 users per second, we would be totally fine, because once we reach the threshold, we would have enough time to start a new server. But usually servers take some time, more than a minute, to be ready. So in our case, we calculated that would take about a minute. So our limitation in this case, we can visualize it in the chart. Our limit or maximum capacity would be 5 users per second, because that would mean that by when we reach the server capacity, which is 400 users, the gray line, it would have passed just exactly 60 seconds, and we would have another server available. That's probably too close to the limit. We wouldn't be in that situation, so potentially we would need to reduce the threshold a bit if we want to have servers available a bit earlier, or maybe the pace of 5 users per second is not something that we are expecting, then it's not necessary. Then another 2 important topics when building scalable and high available WebRTC applications is sticky sessions and data persistence. By sticky sessions, I mean connections that will be maintained so users already reach the same server all the time. And this is important because when you have a video call or a broadcast, you want to make sure that you are connecting to the right one and that you are sending and receiving the right streams. So it doesn't necessarily mean that we need always to connect to the same server, but all the participants should be able to see the right streams. So that's what we achieve with sticky sessions. We can use different approaches. We could use cookies and based cookies based on for load balancing the specific user. So maybe initially we give a cookie to the client, and then the client will be reaching all the time the same server until the call finishes. Or we can do direct routing through the initial authentication. So we can have server 1, server 2, server 3, and so on, and we connect the user to the right server at the beginning when we authenticate. And yeah, this allows us to make sure the participant is in the right call. And here in this diagram, it's just an example of how a scalable WebRTC architecture could look like, where in AWS, where you have the wrappers. In this case, we just have 2 replicas of wrappers and media servers, and we would have to have a single database where we store everything, and that's why the data persistence is important, because this would allow us to distribute traffic between multiple concurrent services and to recover the sessions in case of failure. So even if there is no failure, we would want that some user maybe is connecting to wrapper number 1 and some other to wrapper number 2, and we want both wrappers to really know what is going on and to be able to connect these 2 users to the same server if they need to. And after that, once we have a scalable infrastructure ready, we will need to load test, of course, and to do that won't be enough to simulate HTTP requests, but we will need to simulate real video and audio traffic. For that type of test, we usually simulate it with spinning up instances that just simulate clients. They just could use maybe Puppeteer or Headless Chrome, something like that, to connect to the specific application we want to test and validate that we can send and receive media. In addition to verifying that we are effectively connected and sending and receiving media, we would also evaluate the performance by capturing information like jitter, RTT, which is round trip time, and packet loss. Those parameters usually indicate more or less accurately how good the video call or the audio call was. And there is also something called acceptable mean opinion score that is also used to evaluate audio and video quality, that can be used as well. And here I just show an example of some statistics that you could capture using just the WebRTC Stats API that is already available in the most of the browsers, and you can get the stats and be able to analyze how this call went, and in this case the load test went. Finally, there are also applications and media optimizations you can use to have better quality and have better experience when scaling. One way is using simulcast or SVC. So we can see it here in this example at the right top corner. How SVC works is that you would send a single stream. It's a technique that you send a single high quality stream with different layers, something like an onion, and the WebRTC SFU will be able to send the right quality of video based on the status of the connection of each participant. So if, for example, user 1 has a great connection, this user WebRTC connection would be notifying the SFU about that, and we would be able to maybe visualize or watch some HD video. But in the case of the second user, he may be using a 3G and doesn't have really good connection. We would get the minimum quality, so would be picked based on, similar to how YouTube works when you pick HD quality or lower qualities. But this is done automatically thanks to WebRTC and the SVC technique. Another interesting approach is just limiting the amount of video. Do you really need video? Some great tools just use audio, like Twitter Spaces, Clubhouse, Slack Huddle. In this case, we can optimize a lot more since audio is much more lightweight. And if we still need video, sometimes we might not need to see all the videos at the same time, so we can just use audio detection to show specific main speaker and be able to scale to much larger audiences. Another typical approach, or optimization I mean, is adaptive bitrate based on resolution. So if the video is small, or the real estate of the web application, for example, is small, we don't want to send HD quality because it really won't make much of a difference. So we could, using SVC, for example, we could say, well, this user resolution changed, we notify the media server, and then that gets updated accordingly. Another interesting one is the Opus Red and DTX techniques. Here I explain a little bit how Opus Red redundant audio data works, and it kind of makes sure that if of sending more audio, so we achieve better quality. So what we are doing is just sending redundant, as the name says, audio, and that would be covered in the next package. So we can, if one package is missing, we can recover it in the next round, as it shows in this image. So we can see this missing number 2, and then we can we get it again in the next package. And DTX is more focused on optimizing the audio usage. So for example, when you are not speaking, you don't send any audio, and when you start speaking, then it's sent, instead of just sending noise. That's also common optimization. Finally, with that, we almost conclude our presentation. There are many more configurations, options, optimizations that will be available in the future, and I wanted just to mention some. There are great teams of engineers working on different fronts to surpass our current limitation in the WebRTC field and others. And a great example is AV1, pretty already well-known codec, and has been around for a while, but some devices still doesn't support hardware acceleration yet, so it causes some high CPU usage today, and it's perhaps not ideal for all the video calling experiences, but it might be potentially in the future. Another example is Lyra. Another, in this case, is not a video codec, it's an audio codec. And also it is looking pretty promising. Again, it's a new codec, so it's not everywhere. But as you can see here in this open source results that Google shared, we can see that Lyra quality matches very closely with Opus, and at the same time achieves much lower bit rates, which would be great for optimization, as you can imagine. And there are additional things like machine learning optimizations that people is using and is even being used today in things like Google Meet to do noise reduction, or even packet loss concealment, which is basically simulating making it like a smooth transition when there is some small glitch, or maybe some audio doesn't arrive specific package, instead of just breaking the flow of it, making it filling the gaps basically of the packets that aren't received. So with that, here concludes our presentation about architecting your WebRTC application for scalability. I really hope you enjoyed and learned from this presentation. And if you are interested about this topic, visit us or follow us at Twitter. And thank you so much for watching.